So the format for today is going to be a little bit different than last time.
Recording?
I did. Recording has started. Thank you, Jim. Last time I made slides. This time I'm doing it all live in VS. I have to respond to the admitting people in. So I have a few different files that I sort of set up that we're going to walk through those files. This will let it be interactive. We can run the code. We can make changes. Have questions. I think I'm getting a little echo from you, Sil. Is that all legible, readable up there? People okay with that font size? Sweet. We'll dive into it. So we're starting today with me saying I was wrong and lied last time. And I'm really mad at Shane. Everybody boo Shane because he didn't correct me. And I feel like he knew I was wrong. I was wrong about how Rust deals with the sizes of slices at compile time. And specifically the length of the slice, there is a type of array and a type of slice with a known length at compile time, but the default one does not. So the first little file I've prepared here is walking through some specifics of slices and stirs and the stir versus string type and digging into it a little bit. So kind of similar style to last time, I'm just going to start going down the file line by line and talking about what's happening on it. On the first line, I'm initializing A to be an and stir. So it's a reference to a slice of bytes, and that slice of bytes will be static data in my executable. On the next line, I'm creating another variable that is of string type, heap allocated, and I'm doing that by calling the toString method on astir. That is not consuming astir. If we actually go into the toString method implementation in the standard library, the toString method takes an and self and is actually creating a new string. So that is not consuming the previous string. Both variables are valid there. So again, stir is a slice containing both a pointer to the memory and the length of the region. I wrote some little Rust pseudocode here to try to represent kind of a way that the compiler could store that inside. Both the pointer and the length are determined at runtime. Because of that, the size of stir is not known at compile time, and you can't directly put stir into a variable or into a memory address. Stir is a type in Rust that does not have its size known, and therefore we only interact with stir in most circumstances through a reference, because a reference is of known size. Does that make sense?
So the reference for a C guy is a pointer and a size T.
We can pretend the reference is a constant pointer.
Okay.
The reference itself doesn't contain the length. The slice contains the length, and we have a reference to the slice. Sorry, that's annoying. On this line, then, I'm creating the substring here by referencing a subset of the bytes in it, and the type on the left is still answer, totally normal here. Now, what happens on these lines if I try to make a reference of fixed length? So this would be a reference to an array of a fixed number of bytes. And here's sort of two different ways that might be written in Rust to do what I was claiming was happening last time, where I was taking a slice of fixed size with that size being tracked by the compiler and as part of the type instead of the size being data in the runtime. Neither of these lines actually compile or run. The top line works. You actually take a slice, but here's actually the compile error that I get if I try to do that. On the left side, I'm saying I wanted and U83, and it found slice, bracket U8. So when the bracket type, that is slice. That is what has the pointer and the length. You put the ampersand in front of that. That is a reference to the slice and of known size. I wanted to show this RFC link. It opened, but it didn't take me there. Which is an open change requested to the language, requesting a syntax for how to take a length of size with people proposing different answers for it. And this is still open and still being worked on. There is a array ref crate that someone in the community has written for, but this actual RFC is where the lower syntax was proposed here with a way to do it. That's
The U8 :3, that's itself a type.
Yes, so U8, so I can make here, I can do let array of type U8 :3, and it's semicolon for the linked syntax, and then I can say that equals 1, 2, 3. And that is a valid array with a fixed length assigned to values, and that all works out. It's giving me a warning here because it's telling me that I declared a variable and never used it. One of the nice things about doing this live, we can see all the little type hints and compile hints as we go. Prefixing the variable with underscore tells it, hey, I'm intentionally not using this.
So if you omit the type hint, will it correctly infer U8?
Let's look at line 24.
Oh, look at that.
Where I'm directly assigning it. So by default, if I don't specify the numeric type, it is by default I32. And so these numbers are being interpreted as I32. I think I can do as U8 like that, and the inferred type will jump. And I only have to do it on the first one because arrays by default force it to be one type consistently through it. And here again is I'm taking a slice to a chunk of that data. If I try to get rid of this ampersand here and do this, it's going to say it can't compile. And if I hover over this, it will say the trait sized is not implemented for square bracket, integer, square bracket. And the trait sized is the way that the compiler talks about the compiler doesn't know the size of this data at compile time. And so we stick it behind a reference, and then it does know the size. We'll talk a little bit more about traits going on, but here's the chunk that I think is really salient here of square bracket I32 equals an owned array of I32 of any length, including 0. The size of that data is unknown. And that is a length, that is a set of memory of any length that doesn't know its size. That means like owning that memory is really hard, because if we were to then drop that variable, how would we deallocate it? We wouldn't know. And I32 is the borrowed slice of that stores the start and the length, and then here is a fixed size array and the syntax for that and the types for it. Showing some of the functions inside of Rust that kind of let you peek inside and look at some of these things. Standard mem size of val is exactly like size of in C++ or C. It does the same thing. I'm showing you what this code would print out when we ran it right here. So this is, again, referencing this array on 24, which is 4 32-bit values. Or yes, so 4 bytes per value, 4 values. This will tell me the size of that is 16 bytes. The size of the slice of a thing referencing the chunk of it, regardless of how much of it I slice, it will always be 8 bytes, because on the target compilation architecture, the target I'm compiling to, the size of a pointer will be 64-bit. This can actually be a different size when we are compiling for a 32-bit system. Questions there? Oh, Jesus, it teleported. An interesting thing we can do, it is completely legal at any time in Rust to get the actual memory address of a reference. The as pointer function is defined on anything that is a pointer, and will spit out the actual pointer type for it. Specifically here, *const t, that for C++ people, that syntax will look damn familiar. Yeah, that's a const pointer to t. You are allowed to get the pointer anytime you want. What is not allowed is dereferencing a pointer. If you try to actually use that pointer for something, you've entered unsafe code. And to dereference a pointer requires you to use the unsafe keyword and manage that memory yourself in a safe way.
So I'm assuming that if you send it to C code, if you take the pointer and send it to C code, it's also need to do the same warning. Do you also need to wrap that in unsafe?
No, I'm allowed to send it to other C code, but what am I allowed to do with whatever that C code returns to me? Or actually, I think Shane.
Say anytime you call it FFI.
Yeah.
C could sure clearly do that.
Yeah.
Just making the external calls.
Great.
Okay.
Yeah.
What
Thank
if
you,
you
Shane.
give the pointers if you can't dereference them?
People do a ton of shit in unsafe contexts. It can be totally valid to write a library. Like, let's say we want to implement our own mutex. We can do the low-level pointer manipulation ourselves within chunks of unsafe code that we, the developers, say we've checked this correctly. A lot of the powerful libraries in Rust will be doing unsafe things in their very core, but some developer has done that unsafe code where they've checked it to the standards needed for the compiler to know it's safe and wrapped it correctly. There's a lot of debate in the Rust community about how much unsafe code is good or acceptable. The Rust language creators keep creating more and more types and more features of the language that let you need less unsafe code because like the standard library is wrapping it for you well, and people want to use that. There's a fairly famous crate in Rust, which is called Actix, which is the fastest web server anyone's ever written, and currently dominates all the web server benchmarks, and Rust is very proud of that. The author of Actix got in a flame war with the Rust community because he wrote a crap ton of Actix using unsafe code, and then people kept filing MRs to remove the unsafe code out of it, and he said, I like the unsafe code more, and refused to merge their MRs, and there's kind of like a flame war in the Rust community about how much unsafe should there be in a library, and it depends on it. Like if you choose to do an unsafe block, you're just stepping into C. You're letting go of the rules. You have to check it yourself.
No, there's more rules.
There's more rules than C. Fine, but it's you have to safety guards are off. Let me actually run this code to show running it. So I'll pop into a terminal. I'll do cargo run -- bin, and the name of this binary file here is it. So it actually just compiled and ran it. Here is the result of the print line for size of array. So we can see 16 and 8, like I said. Here's their actual addresses printed, and it's exactly like I said. The slice is pointing to the same place as the array is pointing to when we sliced from the 0th character. If we sliced from 1 here, the slice will actually move one address further ahead. We can also look at length. Length is just a property of it. So like it knows that that slice isn't just a reference; it's a reference with the length. It's carrying its length with it, so we can get it. This is where things get annoying in Rust, and I really like it, but it's kind of crazy. Stir and U8 are very, very similar types. Whenever you see stir, you can interpret it as the same type as bracket U8, with stir having the extra restriction that the bits inside of it must always be valid Unicode. To construct a stir or manipulate it or assign it to a variable, you are never allowed to do anything that would make the internal bit pattern not be valid Unicode. And there are, bit patterns that can fit into a U8 which are not interpretable as Unicode. So here's an example where I'm saying,
when you say Unicode, you mean UTF-8?
UTF-8, sorry. I don't know well the distinction between them.
Windows.
Okay, sorry. Yeah, UTF-8. I'm making a string here, and I have directly typed the poop emoji because you can in Rust. All the source code itself is UTF-8. So there's a poop emoji. What happens now if I take a poop emoji and I slice it from 0 to 1? That panics because that poop emoji is actually multiple bytes. It takes more than one U8 to represent that, and if I try to split that poop emoji into just the first byte of that poop emoji, I no longer am creating valid Unicode, and I can't store that in a stir. So the correct way to get the first character out of a string is actually this method where you call the chars method on it, which returns an iterator over the valid characters of it. Char is also a fundamental type in the language where char is a valid Unicode character as Unicode defines a character. And if you've not dealt with Unicode a lot, it's very confusing when you try to do string manipulation in Rust. If you have dealt with Unicode a lot, you're like, think fuck a valid API for it that actually keeps me from shooting myself in the foot. Here again is me printing my fantasy slice, and we do see a poop emoji got printed in the output, so that's pretty great. I did want to show here, oh, why does it keep teleporting around? I don't know. I'm declaring a function here. For anybody paying attention, we're actually inside main. I'm declaring a function inside another function. completely valid in Rust, and that function's scope is then only exists within this function. So I can only call it from within here. I'm showing you that I have a function here that takes in a reference to some U8s and takes in a fixed size array by ownership. And that's completely valid. And I can call it with a reference to some data and the actual data. In this case, when it is taking it by ownership here without a reference, remember that at the end of this function, when this curly brace is hit, it will destruct that variable and actually free that array from memory. I wrote this function mainly to show you what happens if like we try to call the function without having taken a reference to it. It's telling us it expected a reference to a U8. It found an array of integer semicolon 6. The brace integer syntax that we're seeing in some of these compiler errors comes from the fact that if the function I was calling specified a particular type of integer, it would just assume, because I didn't specify the type in the array, it would do the type inference backwards and set the numeric there. And then I wanted to show if we do try to pass in a reference into where the function is expecting owned memory, we'll get a different compiler error, and it will look like this. Let me actually compile that to show you it as the compiler prints it out, because my God, does it print out good error messages. Mismatched type expected F32.3 found reference to float 3. Arguments to this function are incorrect. Function takes slice here, and then it literally gives you the diff of, I think you meant to put an ampersand there. Mwah. Mwah, compiler errors. Very good. That's just the primer on slices and string explained a little better, because I think I didn't do a great job last time. I feel like I still didn't do a great job this time, because I just think it's complex inside of Rust, but hopefully that helps. Pause there for questions.
It's complex, but what they're trying to accomplish is complex too. So
Yes.
the fact that you can do all of this and have compiler checks is impressive.
Yeah. Yep.
So the string type, or the stir type, is a slice, or it has a slice, or
Stir written like this is literally it is a U8. It is exactly this. Like they're equal to each other, but they've wrapped U8 by the compiler in rules that say that the bits have to be valid Unicode.
Right.
So like the underlying representation of stir is exactly that, and nothing else.
But that is a primitive from the compiler's perspective.
Yes, and they have done some slight magic in the compiler to implement stir that you could mostly implement it the same, but with some restrictions if you did it yourself. There are like 8 other string libraries in the Rust ecosystem that people have written for very reasonable reasons of like interacting with operating systems and lower level. And there's a C stir type for when you're interoperating with C and you want a null terminated valid ASCII string. There's reasons. Slightly annoying, but again, like it's doing a lot.
I have a question.
Yeah.
But it's based on the syntax you wrote there for the function inside the function.
Yep.
So putting my compiler hat on, you have the function is then an expression. Does that mean you can assign it to a variable?
Yes. There's a slightly different syntax for it. So if I do let a equals takes slices, and I don't do any of this, it auto-completed that for me. Here's the type of the function, which is fn takes slices with those arguments. And you can see the name is included in there right now because it is specifically the type of the return of that name is unique to that variable as it stands. There's a slightly different syntax, which is like I could do let b equals, and if I wrote it like this and U8, comma, bracket, F32, semicolon 3, bracket, like this, I've now written a closure, an abstract function.
Okay. So that's like a lambda in Python.
Yes, exactly.
All right. So then that was my next question. Is this syntax can only be used to make lambdas, or can you use it, look, we see what type def, where any possible function can fit into a variable of that type? Or is it specifically a variable of a type that points to that one specific function?
Any possible function can fit into a variable. When I do this syntax with the vertical pipes here, that is a anonymous function that does not have a name and can be anything. It gets even crazier because there's two underlying types in the language where there's a capital FN and a lowercase FN, and it's the difference between a trait and another thing. And we'll poke at it a little bit, but you're going to see the trait system and get a little crazy. But a thing I could do here, where like the type of A right now is specific to that take slices function, I can write this slightly differently, and I can tell it that I want the type to be FN of something which takes and U8 comma bracket. Why did I pick one with such a complicated signature? And that's valid. And now I've said I want the type of A to be generic to any function which implements that interface. I could put take slices on this side, or I could put a closure, or I could put anything which has that same function signature there, and that's valid.
And closure is just opening a set of mustache brackets.
Mustache. Closure specifically has these vertical pipes. This is like the most basic closure. That's like a null closure that takes no argument and returns nothing.
You need the pipes, and then you have.
Yes, and when you use the pipes, it's anonymous. It doesn't have a name. There is no way to refer to it by name. You can only refer to it with a variable. If you use FN, it will have a name.
And then, so after you have the pipes, does it have to be a set of expressions enclosed in mustache brackets, or can it just be like a single line?
Oh, it can be a single line, yeah. So we can do, we'll do like A is equal F32, and then I think we can just do like print line A, like that's should be completely valid. Why are you mad at me? Oh, I forgot quotes. Oh, yep. Let's jump to types.
Okay, one more question.
Okay, sure.
So back in your null function example, can that function, or can any of these functions reference variables in the scope above them?
No.
Okay, so the null function, like barring unsafe code, couldn't possibly do anything, like couldn't have any side effects aside from, I guess, printing.
You can move variables into a closure.
Yep. So okay, so this is gonna be next. So I'm gonna say let x equals 4, and now I'm gonna make a closure z, which is equal to move bracket thing here, and I can say print line x, and the closure, while taking no arguments and returning nothing, actually stores x and owns x, and when the closure is deallocated, the closure will drop x. And so exactly like you can embed data inside closures in C++, you can also do it in Rust, and just by adding this move keyword, it is moving x inside the closure, and the closure now owns x. So there's a backdoor to get data inside.
Okay. One more question on the functions as the higher order.
Yep.
Could you get the name of the function, such as if you pass in the name function takes slices, is there a way to get its name?
I assume there is with some standard library invocation. I never have. And with that name in a variable, you couldn't do anything with it. Like the name is only valid in the compiler's context.
Okay. Yeah.
You could print it for debugging, probably, but you like dereferencing that name to look up the function again, crossing like DLL boundaries, don't fuck with that. Don't go there. Okay. Those were great questions. We can spend a lot of time on generics and lambdas. I want to talk about types and traits. We've already talked about types a lot, but now we're going to introduce the concept of traits, which we already saw a little bit with that sized trait, but trait is how Rust deals with all dynamics, all generics. I'm starting at the very top here, and I'm defining two structs, and we can imagine this is some service where I'm going to call a request time service with no data. It's going to return to me the time. Like that's an API. I'm going to put in one type. I'm going to get another type out. I just needed a couple example types to work with. I'm also just bringing up here that empty parentheses is the null type. These are also valid ways of declaring it. Like lines 10, 11, and 12 are all syntax equivalent to each other. They represent the same type. The empty parentheses, you should just think of as a tuple of 0 elements. Because if I can also say, like let a, I'm doing this not inside a function here, let me make a function, fn dumb. I can say let x equals f32 with parentheses like that. Nope, sorry, 1.0. The type of x there is float f64 by itself. If I go like this and I say like a, I've now made a tuple of a float and a thing. So tuple is a fundamental type in Rust, and tuples are very easy to work with. That's just an easy way that I remember why the null type is an empty set of parentheses. It's a tuple with no elements.
Wait, so Rust have vectors too, right?
Yep, vectors, arrays, and tuples. Sorry.
Vectors, all of the elements inside the vector have to be the same type.
Vectors and arrays both have to have all the elements be the same type. Tuples can store an arbitrary collection of types. And you can basically, a tuple is equivalent to a struct with the names of the elements in the struct being .0, .1, .2. Yep. Okay, so I want to implement something useful actually on these types. I made 2 types. I want to do something with them. I want to be able to print them. So I'm defining my own print function for them that will take a reference to themselves and return me a string that I can use for printing them. This is the very basic naive way of doing that, where I just manually define a print function on both of them. That works great. And then here is an example of me in a function. I'm creating a request time object, I'm creating a time response object, and I'm printing them both by invoking their print functions and sending those strings to the actual print line. Makes total sense. Not very useful. Like, great, I wrote some functions and I called some functions. Nothing fancy or useful happens here. I want to do something better. I want to be able to interact with these types in a generic way where I could do the same thing on any type which implemented something. So what I do is I define a trait. The trait here that I've decided, I've named the trait printable. It has one function in it, which is print. It takes a reference to self. It returns a string. Any type which implements this trait must give a definition of that function. Questions there? Okay. I'm now going to manually write the implementations for my types. And this is where like the impl syntax starts to make a little sense. So previously we just saw impl request time. Now I'm saying I am implementing the trait printable for the type request time. And so for this type, I'm providing a definition of printable. Does that make sense? There's my print functions. Cool, great. Now I can generically do things with them, which is fucking cool. So let A equals a vector of a reference to dime printable. And then I'm saying it's equal to a vector of a reference to request time and a reference to time response. That's completely valid. I can now say for item in A, item.print. And that's completely valid and completely works. I'm gonna let that sink in, and I'm just gonna let the first question come.
Why does it have to be dime in this case?
In this case, the dime keyword in Rust means dynamic dispatch. And it is the difference between at compile time dispatch and at runtime dispatch. In C++, this is the difference between a templated function and a virtual function. In this case, the type dime printable is a fat pointer that includes a pointer to the original object and a pointer to the impl table of that trait for that object. So it knows where to find the types. This is exactly how defining a virtual function works in C++ and how the V table works in C++. So in this case, what I'm actually storing here are references to fat pointers that tell me where the object is in memory and then where the implementation of that trait on that object is. And then I can call it, and it just works.
When you call print, are you calling the ones you defined in the printable block or the ones above that?
Good question. I'm calling the ones on the printable block. And that's because of what's going down here. So can I do other things with this type? Can I print it? Can I clone it? No, because in this context, the only methods I'm allowed to invoke on it are the ones that are coming from that type. The only thing I'm allowed to do on this type right now is what printable lets me do on it, because I don't know anything else about the objects. I've erased all other information about them and only have access to the interface provided by printable for me.
So the original print definitions still exist?
Yes, this is gonna be slightly funny. This is annoying syntax. It does exist though. So I'm gonna say let a equals request time here. Just like that, I have an a now. If I call a.print, or I'm gonna say let stir equals a.print, which function am I calling? I'm calling the one on the type itself by default. If I want to call the specific one on printable, there's a different syntax here. Shane, you might have to help me out. I think it's going to be printable : print.
Oh yeah.
And then I'm going to pass and a in and call printable like it was a static function, but manually passing the reference in. And that will call the two different versions of print that I've previously defined on it.
So if you hadn't defined the first print implementation, would a.print find the printable one?
Yes, it would have. So there can be like name shadowing, but there's a very, very defined way of how the name shadowing is resolved. It is not overloading, but it kind of looks like it if you squint. To talk about it again, if I tried to make this instead, where I drop that ampersand and don't have ampersand dyn printable, we're getting this trait size is not implemented for dyn printable again. The compiler does not know how large the memory owned by dyn printable is. You can't own it. If you owned it, the compiler wouldn't know how to allocate or deallocate it because it's things of different size. So I have to hide it behind something that hides the type, that hides the size for me so I can interact with it. Dyn trait for anything doesn't have a size known at compile time. That's an important thing to know. Reference to dyn trait does have a size known at compile time. The size of a reference is always known. Okay, so now we saw dynamic dispatch. We saw at runtime, I could have shoved anything that was printable into that vector. It would have found whatever was printable and at runtime called the correct function. Let's do it static dispatch now. This is the compile time version of that. Can anyone tell me why this code won't compile? Not Shane. Here's a hint.
So the way you specify that type doesn't have any notation associated.
Yep, I have said I'm taking a completely arbitrary type. It could be any type in the world. And now I'm trying to call print on it. Well, every type in the world doesn't have print on it. So I need to tell the compiler when I'm taking a generic type, what traits I am demanding that type have for this to be valid. Printable. That compiles. And so I'm saying now I'm writing a generic function with a generic type. I will work on any type where that type must implement printable. And then this function is completely valid. I'm taking that type by ownership. I'm using its print function. I'm sending the string it returns to the line. We've now written a generic function in Rust.
All right, so some languages that do this sort of thing have a top level interface, any or object or something like that, that sometimes has functions defined on it. Is there anything like that in Rust?
There are a few, but ever so few. So if I go like this and I say ampersand here, I'm specifically going to take an ampersand type here to just show a few of them, and I say item dot. Here are the functions that exist on any reference. So for any reference, I can clone the reference, I can clone from, I can clone into, I can call this into method, I can try toOwned to take ownership of the reference, and I can call this try into method. So those are traits that are implemented for any reference that are brought into scope by Rust by default. There's a thing we haven't talked about yet called the Rust preamble, but there's a little chunk of Rust code that auto includes a bunch of things for any Rust program that you have to opt out of, where by default, like vec is brought into scope. These are coming from that preamble, where these are traits that the language has defined for any type whatsoever. In this case, these are all traits on references specifically. If I make this not a reference, where it's just truly an arbitrary type, and we look at what functions exist, it is two. Into and try into are the only ones that Rust provides in its preamble. Not to say if anyone else wrote a trait that worked on any type, and I had imported that, included that into scope, those functions would also show up there. Sorry, that got probably a little deep, but this is totally valid. So now I'm actually going to show you 3 different syntaxes for the exact same thing, because Rust is opinionated about some things and then gives you 3 different ways to write it in other places. I find it annoying, but there's reasons for all of them. This syntax here on line 95 with impl printable, they added this as a shorthand later in the language's life to just save you time. In this case, I'm not saying there is a type T and that type T implements printable. I'm just using an unnamed type and saying there will be a T here. If I did, I could do something like this where I put in another item 2, and I said impl printable as well. These can now be 2 different types. Like this would be T implements printable and G implements printable, instead of these 2 having to be the same type when you called it. But impl is a shorthand for just, there will be some type. I'm not going to name what that type is. That type has to implement printable. This is the style I just showed you, where I'm putting the guard, the trait guard, directly inside the brackets. This can get really ugly when sometimes you have like 15 things in here. So we can put other traits in here, like clone and debug and display, and plus is how you say and, it must implement. That just got ugly at some point, and so they decided to add this syntax where instead of putting the guard directly here, at the end of the function you can say where, and then put the list here. They're exactly identical to each other, but they keep the code from looking as ugly.
Except it's like a where you just commas.
Sorry, the comma there is actually optional. The comma would be there for like H, with H being another type. So the comma would indicate that T has ended, and now we're specifying it for H. I like to always have trailing commas just whenever I can. Helps with my get diffs. So let's talk about some of the traits which just are in the standard library and super common to encounter. We're also going to take our first glance at actually looking at some Rust documentation. So this is the documentation for the Rust language itself. There is a trait in the standard library called default. The trait is defined like this, which uses a slightly different syntax than we've seen before, where there is this capital S self. That is saying the type that it is defined on. Zoom in, make it bigger. Okay. Yeah. This means if I implement it on my type, what this function is going to return is my type. It will return the type it's implemented on. That's what capital S self stands for. But this is a trait for giving a type a useful default value. Any type that defines this, then I can call default on that type and get a default constructed version of it, which is super useful. Here's what it looks like invoking it. So I can say let options equal some options default, and the Rust compiler knows everything it needs to know to default construct and return me one of those there. Pause for questions.
Is capital S self the type of the object itself, or is that the what it implements?
It is the type of the object itself. So if I say trait, my trait, and I'm going to say it has one function on it. The function is named my new, and it returns self, like that. And then I impl my trait on for what was one of the types I named at the top here called request time. Yeah, for request time. First off, so I have an empty implementation here. What's it mad about? If I hover over it, it's saying not all trait items implemented, missing my new. I don't have an implementation for my new. I'm going to do a autocomplete in VS Code, and VS Code will automatically fill out all of the members for me, and it will put this to-do in. That'll panic if I actually try to run that function, which is great. But now I'm going to return a request time. So in this case, self is referring to request time. In this case, I don't have to use request time. I could have put request time here, and that's the same. Self and request time are the same type within this context. Here, I don't know the name of request time, right? Like there's no way I could say it other than using capital S self.
Wait, so there's in that second block, would lowercase self return my trait?
Self is returning, self is this. Self is a pointer to the object. In this case, I'm not taking a self in, right? This is a static function, so it takes no arguments. I don't have an object to operate on, so I don't have a self to return. If I tried to, like self here isn't a type, self here is a, self is the name of a variable. Capital S is the name of a type.
Just for my clarity, is it like Python where self, it doesn't have to be called self, that's just a function, or does it have to be, the variable has to be named that?
Let's do it like this. So if I do impl, if I'm gonna do another impl block on request time here, and I'm defining new functions on request time, and I'm gonna make a function, and I'm gonna call it weird new, like this, and I can say and I'm gonna say a equals and request time, like that. I can write that function. And now I can operate with a, and a is a reference to a request time. If I do that, and then I try to actually call that function, so I'm going to say fn calls weird. If I can spell, sorry, this is a longer explanation than I probably want to give, but I think it's good. So I've constructed a request time now. If I call b.weirdNew, it won't do anything. That function doesn't exist. I would have to call request time : weird new and pass b into it with this like static function syntax for it. That's valid. If on the flip side for weird new here, if instead of saying naming it a and saying and request time, if I had done and self, then both of these syntaxes are valid.
Yeah,
so,
okay, so self is a keyword, basically.
Yeah, self is a special case, and self matters where if you do self, this dot operator works, and dot is just automatically putting b as the first argument there. Sorry, if you worked with C++ calling convention, it's the same tricks are possible in C++. If you've not seen it before, it's just a mess. Talking about these other traits, just to quickly burn through them, there's a display trait. Display is the trait that we've been using whenever we passed something into print line. So when a trait implements display, it implements this format function, which handles all the ways that we turn things into strings for displaying to a user. And once a type implements display, we can pass it into the format function, the print line function, the print function, and that whole system knows how to convert it into a string. There's a really similar trait called debug that actually has, I think, the exact same signature. The difference is that you have to choose to use this colon question mark syntax there. That's telling it I want this thing printed as in debug style. Debug is designed to be useful for software developers, but isn't like a canonical representation of this as a string that I would show to a user. This gets kind of pedantic and into like the low levels of how you should display strings to people. But for instance, vec and array define debug. They define a way to print them for debug. They do not define a display implementation for them for that. So you can print them for debug purposes, but the Rust ecosystem is like, hey, there is not a canonical way to display an array to a user because different cultures order things differently, top to bottom, left, right, up, down, backwards, commas mean different things. So there's only a debug implementation. Another one which is good to know about, we've seen it a lot before, but we'll look briefly at clone. Clone defines two functions on it, clone and clone from, where clone takes a reference to self and then returns capital self. So that is the function that makes a copy of something. Clone from takes a mutable reference of something else, and it's slightly weird. We're not going to dive into clone from. I just wanted to show you a lot of the things that we've been doing before when we're making copies and we're printing things are these traits that we're interoperating with, and we have generic functions. So putting that all together, here's a generic function that's doing a ton of things. So it's taking in a T, the input is T. T has to implement clone and display and debug and default. And that means we are allowed to clone the input that we got and put that in a new variable. We are allowed to construct a T from default. We are allowed to print it as display, and we are allowed to print it as debug. All of those things we can do. A thing to know here that's kind of funny, that is inferred in the Rust ecosystem. So right now, T, look at how that list has 4 things in it, and then below that, VS Code is showing us 5. Why? Because sized is in there. By default, all types implement sized, and you have to intentionally opt out of sized. So if I wanted to take in a type or operate on a type where I didn't know the size of it, you do this weird syntax and I say question mark size, and that says not sized. And then I can write stuff where I can write functions even on shit that doesn't take sized.
Is it question mark or exclamation point? And question mark is maybe.
Sorry. I think it's question mark. Yeah.
It's unpinned, which uses like.
Yeah, question mark is not sized. I didn't make the language. I think it's pretty good, but I didn't make it. Okay, we're gonna extend this even one step further, because there's even more generic. We can go further. So I'm making a trait here that is called sarcasm display, which says this type will have one function. That function is sarcasm. It will take a reference to self. It will return a string. Now check out this bad boy. Impl, and now the impl block is generic. And I am implementing for any type T that implements display, sarcasm display for that type T. And then I'm saying sarcasm goes to string because sarcasm implements, because the type T implements display, I can pass it into the format function and I can wrap it in my little sarcasm HTML pseudo bullshit to put an implementation there. I have now taken any type that previously implemented display, and when this impl is in scope, when anyone includes it, in my module it's included, I can now call sarcasm on it. So I can show you use sarcasm here, and I can call sarcasm now on a string slice. I can call it on a number. Can I call it on a vector? No, because vector doesn't implement display, what I just said earlier. If I changed this to debug, and then change the syntax in here to colon question mark like that, I can now call it on a vector. And I implemented sarcasm for any type that implements debug now. Holy shit, that's powerful. So you can write generic implementations where the implementation operates on traits. And this allows you to extend other types and do all kinds of crazy shit. There is a restriction here. And it's a very good restriction, and it's to keep, what you don't want to have happen is I don't want to include some code and some fucker in that library that I included implemented a super generic thing that then fucks with all of my types that I included from somewhere other place. I should swear less. This is going on YouTube, sorry. I don't know if you've ever worked in like the Julia ecosystem or the R ecosystem. Packages love it when you include them to override the vector type in the language with that package's implementation of vector. Rust doesn't want that happening. It doesn't want things doing it. So there's a limitation that comes with traits right off the bat. You can only implement a trait for a type if either you're the author naming the type or you're the author naming the trait. So you have to own the definition of one of those two things to be allowed to implement it. So if I try to implement display, which is a trait I didn't define, for vector, which is a type I didn't define, the language will give me this wonderful compiler error. Oh, let me actually compile it because VS Code's not being happy. Oh, I compiled the wrong program. We are currently in basic types. Here's the compiler error. Impl doesn't use only types from inside the current crate. Note, define and implement a trait or a new type instead. Only the traits defined in the current crate can be implemented for types defined outside of the crate. If you understand what that means, it's kind of hard. So there is then a way around this, and it was talking about it there. It referenced new type, which is just you can wrap a type in another type. So here I'm saying I'm defining a struct. The struct's name is myvec. Myvec is generic on any type T. Myvec is actually just a tuple with one element where the thing inside of it is vec of T. I have created a name now where myvec has everything that vec has, but it's my name for it within my crate. And now I can implement display for myvec totally generically. So this is called the new type paradigm, where you're just wrapping someone else's type in your own name for it. And then people can choose to refer to your name for it or their name for it if they want to opt into or out of it. So if I say let vec equals myvec answer, myvec equals this thing, why are you mad at me? Oh, sorry.
It's, did you change it to debug? With it?
Oh yeah, sorry. It's because I did debug up here, and I'm mixing debug and display down here. And so the fact that your type implements display, it doesn't also implement debug. You can implement one or the other. Implementing one doesn't automatically implement the other one. If I can either swap debug up there, or I'm gonna swap debug in down here. Wait, no. Yeah, that's it. Okay. No. Yeah, good enough. Whatever. Moving on. Okay, so last thing, we've seen some macros in Rust before, like print line, exclamation point, here's a macro. Macro is compile time code generation. Macros are super complicated in Rust, and we're not going to rip them open and dive deep in them tonight, but I did want to show you this Derive macro, which is the best motherfucker in the lanes. I'm going to have to beep a lot. It's really, really cool. So Derive is a macro that will auto-implement traits for your types when those traits have obvious trivial implementations. So I can say derive clone debug default hash partially equal partially ordered and ordered onto my type, and I will have default implementations for cloning it, printing it, putting it in the hash map, comparing against it partially, sorting it fully, sorting it partially. And because string and U64 already have definitions for all these types, it just passes along to those and auto-generates all that code for me, so you don't have to write a ton of boilerplate to implement traits. You can make your own traits compatible with Derive so that they will automatically be derived, and that's just very, very badass. That's the whole introduction to basic types. Was that good? Okay, we're at 4 minutes until technical class end. Can I get thumbs up on who wants to just keep going because I have more content prepared? Okay, we'll just keep tearing on. If you want to leave, no hard feelings. We're going to jump into multi-threading because this is where I think Rust truly shines. There are traits in Rust that determine whether or not a type is safe to send across a thread boundary or not. There are two of them. One is send and one is sync. Send says this data is safe to move from one thread to another thread. Sync says this data is safe to be present in two threads at the same time. So plain old data, if it's a string, if it's a number, if it's an integer, whatever, automatically implements send. A lot of types will automatically implement send. There is a default implementation in the Rust standard library where if you make a struct and everything your struct contains is send, the struct itself will also automatically be sent. Sync is not the same way. To be sync, you have to actually be safe to reference from multiple threads, which means you have to have done some wizardry. And so like a mutex type is sync. So here's the first example, shared reference. I have a string and I want to share it between the current thread and a new thread. Can I do that with a reference? So in this case, and we're now seeing this wonderful closure syntax again, I am creating a closure that is a function. I am calling the spawn function, and now we're seeing here's how the Rust library deals with generics, where here's the signature for spawn. Spawn takes two types. a function type and a return type. The input is of the function type. The thing it returns is a type join handle wrapping the return type, where both the type that you're sending in and the type that you're returning have to implement these piles of traits. Oh boy, that seems so complicated if you're not used to it. But as you get really familiar with your types, what is amazing about Rust is that function signature tells me literally everything I need to know about the spawn function to work with it completely thread safe. And the compiler can then enforce thread safety on this type for me. Questions there?
That's awesome.
Okay, so we're getting a compiler error here. And I'm gonna compile this program now. So I'm gonna cargo run threads, and threads will compile for me. And here's the compiler error we got. Closure may outlive the current function, but it borrows string, which is owned by the current function. So right here, it's saying this closure may outlive borrowed value string, where string is the name of this variable, and I'm referencing the string in there. Do people follow why that's illegal? Because that right there is use after 3. I have a local variable, it's named string, I'm referencing it in here, and the compiler can't guarantee that this string will still exist when this is it, and says, you're not allowed to do that. You're not allowed to reference data, which I can't guarantee will live as long as the reference will live, and disallows you from doing that. So when we cross thread boundaries, you can't guarantee the thread that owns the memory will outlive the thread that references it, which could lead to a use after 3. So when crossing thread boundaries, we have to do special things. One is all kinds of data encapsulation. There's special types to work with it. The other thing is like the static type here, where if instead of this being a string, if this had been a reference, and I specifically here, I can do one extra thing here where I'm going to say the type of this is and static stir. Why are you still mad at me? Oh, so never mind. That's a bad example, and I'm not going to explain what went wrong there. Okay. So how do we guarantee? So we're going to show through a series of examples here. We're going to encapsulate types and other types, where those types implement traits for us to get magical behavior. The first one that we're exposing here is RC. RC is a shared pointer in C++, if you've ever worked with it. RC stands for reference counted. It allows me to take as many handles to the data as I want. Every time I take a handle, it has an internal counter for how many people are referencing that data. Every time one of those handles is dropped, that counter goes down. When the counter hits 0, the memory is deallocated. So if I have an RC to a chunk of data, I can guarantee that that data is alive as long as I still have a handle. My handle is guaranteeing that the data is kept alive, and now I can do exactly what I wanted to do earlier, where I am creating a closure. The closure takes an RC to a string. I can print line the closure here. The star here is printing the thing inside the RC instead of printing the RC itself. That's dereferencing it. I can pass my shared string into this closure completely fine. Can I pass it to another thread? I think I've already kind of spoiled that. I can't. Why isn't it showing me the compiler error when I want to? Here's the compiler error. RC string cannot be sent safely between threads. Anyone want to tell me why?
Trait send is not implemented for RC.
Boom! Why is send not implemented for RC string? Why did the authors in the standard library of RC not implement send for it?
You would want sync. You would want that.
Send would be sufficient in this case, but RC does not implement send. The reference count is not thread safe. If I made handles in one thread while dropping handles in another thread, I could have a race condition where I'm reading and writing to the thread count at the same time, and they could become desynchronized. I need the thread count itself to be atomic. RC is totally safe to do a lot of things with, but I can't. So I have a reference count. I have a reference count that is completely safe to use within a thread. But if I want to pass it between threads, I have to have ARC, atomic reference count. And here is the type in the standard library that implements reference count, where it guarantees that that reference count is itself being edited thread safe, and there's a mutex or atomic operations guarding that reference count. And now I have a shared reference that can safely be sent between threads. Mwah! So only if I choose to, and I tell the compiler, I have made this type safe to send between threads and have done it in a way that the compiler agrees with me, am I allowed to send the data between threads and actually maintain it.
Does it do all the dereferencing when the variable goes on scope?
Yes.
So if you send it to a function and the function ends, it'll automatically do it.
Yep. Okay. We're gonna keep the chain going. We're gonna keep the chain going. Okay, so I created an arc new. So arc new around the data of hello string is now creating a heap allocated, governed by this reference counter of the shared string. I'm creating a copy of it. I'm moving the copy of it into this other thread. So there are now two handles. There is the name copy here is one shared pointer. The name shared string is still a shared pointer in my thread. Can I modify it? Oh, I'm not allowed to modify it. And if I say why, cannot borrow data in arc as mutable. Trait deref mutable is required to modify through a dereference, but is not implemented for arc string. What does that mean? I cannot get a mutable reference to the data inside the arc. It will not let me mutate the data inside of it. Anyone want to tell me why? It wouldn't be thread safe. If I'm allowing it to be passed between two threads, it would be unsafe if those two threads, then one of them tried to modify it while the other one was looking at it, we would have a race condition. So arc does not let you in any way get a mutable reference to the data inside of it. It guarantees the data is alive, but you're not allowed to modify it. That's so fucking cool. Sorry. I keep swearing. Okay, so I already put the answer down here. We would need arc mutex string to modify it. Here is a final example of Rust in a completely thread-safe way, allowing me to create shared data, send references to that shared data to multiple threads, and modify that data in multiple threads. So I am saying arc new, mutex new, the number 0. I'm creating a copy. When I'm saying data.clone here, I am cloning the arc, not cloning the thing inside of it. So I have two handles. I pass data into this first thread. I make a second, sorry, I don't know why I reused the name data. That makes it confusing. T1 here is what's being moved in here. T1, I'm not allowed to do any edit operation on it. Like I am now holding a mutex. If I have to call the lock operation on a mutex, which returns a type of lock result. The unwrap here, you don't worry about that. It's slightly evil. They're even extra pedantic about this in Rust. So what happens if I have two threads and one of them is holding the lock to a mutex, and while it is holding the lock to the mutex, that thread panics? I can poison the mutex, where it's then in a state where it can't be locked by anyone else. Rust lets you handle that case with its mutex type. And the operation lock here can either it returns a lock result, which will either return I have successfully locked the mutex, or will tell me that this mutex has become poisoned and is no longer safe to lock because a thread holding the guard to it panicked. Don't worry about that, sorry. But here's me successfully modifying the data in two different threads at the same time, and there is no way for me to write this code in a way that isn't thread safe. To be able to modify the data to get a mutable reference inside of it, I have to lock the mutex. It's impossible for the data to die because the arc is keeping it alive. I was unable to send the data between the threads until it was inside the arc, and I wasn't able to modify it until there was also a mutex involved. The traits send and sync by the thread boundaries defined in the language just keep you from shooting yourselves in the foot. You can't shoot yourself in the foot if you try. Fearless concurrency is real.
That's cool.
Yeah.
I have a pedantic question.
Absolutely.
So in C++ land, arc would be, okay, so if we've got a shared pointer of a mutex,
yep.
Lock would be a method of mutex, not shared pointer. So in C++ land, I would use like the arrow syntax to call lock.
There is no arrow syntax, and Rust implements auto dereffing. where it will try to dereference the type and then see if that function exists on the dereference of it, and we'll do a chaining on it. So lock doesn't exist on arc, but does exist on mutex. This is of type arc mutex. It will just automatically go through dereferencing until it reaches a type that has the function implemented on it. So you can basically see dot is equivalent to put as many star operators in front of it as you need to find that function.
I think you have to implement deref as well, so arc implements deref.
Yes, and so there are traits that allow you to do a deref, and they are the deref trait and the deref mute trait. Lock is a very, very, very particular function because mutex implements a kind of crazy thing. Lock takes an immutable reference to the mutex. It has to for me to be able to call lock inside of the arc. And then inside of the lock function somewhere, there's a little bit of unsafe code where they are mutating the mutex. Data is changing, and data is changing behind an immutable reference. But that's what's needed to work around the compiler there and do it right. So I'm allowed to acquire a lock to the mutex, and the lock function claims it doesn't mutate anything, but it's implementing a thing the language refers to as interior mutability, where data inside the type is changing through an exterior interface that is safe and says it doesn't change. Which a lot of people try to do in C++ and fail at, but you can do correctly in Rust.
I did that today.
Yeah. So I have just a long blurb here. It doesn't matter that much, but there's a fundamental Rust concept here of type encapsulation, where you will see this in every Rust library, where there will be type inside of type inside of type inside of type inside of type to chain functionality and build functionality of higher and higher and higher level APIs on lower and lower stuff. I wanted to show you here how it doesn't fit on, it doesn't fit on one line here, but this is a real type from the Rosslib Rust library that I've been working on. I have a type. My type is socket. Socket is of type WebSocket string, templated on the type maybe TLS stream, templated on the type TCP stream. So TCP stream wrapped in encryption, wrapped in a WebSocket is my socket type. I can then take that stream type and I can say type reader is split stream socket and type writer is split sync socket. That's actually separating the read half and the write half of that into different types. I can then say I have a client. Inside that client, I have a read-write lock reader and a read-write lock writer. Read-write lock is, you should basically always use that instead of a mutex. Mutex allows you to have one handle at a time, whether that handle is a mute handle or an immutable handle. Read-write lock will let 10 people read from it at a time, but for anyone to write from it, all of the read handles have to be let go. So it'll let you have as many reads as you want, but only one writer at a time. So generally, you'll never see mutex, except in weird circumstances. People generally always use read-write lock. And then finally, I have client handle, which is arc client. So here's what each of those types provides for me as I chain them together. TCP stream gives me super low level, here's a TCP socket read write on it. Maybe TLS stream wraps that where it can either be just a raw TCP stream or there can be encryption and it handles all the encryption for me. Then I can wrap that in WebSocket stream to make it an even higher level API to work with. I can then wrap those types in split stream and split sync to get separate read-write halves for it. I then wrap that in mutexes to make sure that I can share those read halves and write halves across multiple threads. And then Arc guarantees that those client handles stay alive. And now I can pass around client handles anywhere in my Rust application, anywhere I want, and those client handles can attempt to read and write from that socket, and it will handle the encryption. It will make sure the client stays alive, and it will make sure that there's never a data race. And that's just mwah. These types also all come from 4 different libraries. Mio provides the TCP socket. Tokyo provides the maybe TLS stream. Tungstenite provides the WebSocket stream, and the standard library provides the read-write lock and the Arc. I will say that I actually think there's a 5th one in here because I'm not sure where the split stream and split sync came from. But all of these library authors wrote completely generic functions on completely generic types, where if these types implemented these traits, they would be intercompatible with it. And that means I can compose like a motherfucker. God damn it, sorry. It's again though, like this WebSocket stream will template successfully on any type where that type implements the API it needs to do what it needs to do. And the same thing with the TLS stream, and the same thing with the TCP stream, where they write these trait bounds and say, if your type implements these interfaces, I can work with you. And oh boy, it lets the whole ecosystem do some crazy powerful things.
Are those namespaces on those before the 2 colons? Tokyo Tungstenite?
Yes, sorry, yeah. In this case, I copied this directly. The equivalent here, like I can either fully qualify the name, or I could have said use Tokyo Tungstenite WebSocket stream to bring the like if I said use Tokyo Tungstenite WebSocket, oh look, it's autocompleted for me. That would have brought the full type into use, and I could have just said WebSocket stream. When I'm saying Tokyo Tungstenite WebSocket stream, I'm saying go look in that crate and then use that type from it. Pause there.
Do you have to explicitly import the crate, or does it just knows?
Yeah, we haven't been showing any of that. Everything I've been using right now has generally been from Rust. There's actually a use block here at the top, and from the standard crate, from the RC module I was using RC, from the sync module I was using arc and mutex. That's how those types were brought in. There's a bunch of types like vec that are automatically brought in by the preamble. But if I wanted to add a crate, like Shane, what's a good crate to add really quick?
Num traits.
Sure. What's a version for it, Shane?
0.1. I need a dash between them.
The num traits is a crate that exists in Cargo. Rust Analyzer is getting really mad at me right now because it's failing to parse the cargo.toml as soon as the cargo.toml doesn't have errors in it. The Rust Analyzer crate now understands my workspace again. The num traits crate is being pulled, and it's recompiling Rust's Analyzer's understanding of the crate with that crate having been downloaded and in scope. And then if I went into where we were a second ago, and I could say now use num traits, num dash traits. What does it have inside it?
Underscore traits.
Num underscore traits. Now it's auto completing. And here's what's inside the num traits crate. And if I control click now, I can actually go inside the crate VS Code because Rust Analyzer parsed it, now knows where it is, and took me right to whatever. I checked shift right, which is a very low level primitive for some crazy people who want to do some bit hacking on some low level stuff. So that's a function, that's a trait that says I'm allowed to bit shift right. I'm allowed to attempt to bit shift right this type, and it will return an option telling me whether I bit shifted right or failed to bit shift right because of whatever craziness.
I'm sorry. You go.
Are there like collision possibilities with these traits?
Yes,
So
and
then you specify. Like,
yep. And it looks exactly like Python. Like I can say import this. I think I can just do as name to rename something that I'm importing if there's a name collision. If the compiler ever can't determine, it will fail to compile. It won't automatically choose one when there's two traits. There is some precedence there where it will find the like if we saw this earlier where it called print on the type itself before it went to any trait, like it will do that. But if there's two traits from two crates at equal precedent, it will fail to compile if the names are collide.
So because of the focus on safety,
Yep.
and all of this being integrated, like the Rust Analyzer, everything's being integrated, you have a toml file. Is there a way to say that I want to use this crate only if it has no unsafe code in it? And as a way of saying that, like, I can know when I write this code that if the author of that crate changes in the future, I don't have any problems.
I don't think so. But when you compile, like remember, you're bringing that crate down as source code and you're compiling it.
Yeah.
You can pass flags to the compiler to say unsafe code is an error. Like you could turn any warning you wanted on as an error when you compile that crate. So I don't think Cargo provides that in the package ecosystem. Like packages in their sort of manifest don't declare that this package includes unsafe code. So you would have to pull the crate and then try to compile with it. But when you compiled with it, you could do whatever you wanted.
I think you could probably do the cargo add-on.
Yeah, a thing to talk about, like I've been using the Cargo command line here. one of the things that you can do is you can cargo install, and you can add commands that people make to the package manager. And people make all kinds of useful packages for doing things like compiling to weird embedded targets, where after you compile, you have to run it through their like special linker and do other things to it. People make all kinds of plugins for the package manager to make it do fancy things like that. I haven't used a lot of them. A very good one is cargo format, which comes with it, which auto formats all of your source code and runs it correctly. We're going to keep going just a little bit further. I'm going to skip. We're just going to do a flyby of box. I talked earlier about using an ampersand as a way to using a reference to hold a type that's not sized. There's an alternative just to know about, which is called box, and box says heap allocate it and actually use a pointer to where it is on the heap. So you're putting the thing in a box. The box is a fixed size. I can hold the box now. Does the same thing as a reference. Box exists, know about it in the keyword. I show examples here of implementing a print queue where it's a vec of references and implementing a print queue where it's a vec of boxes. Yeah, the references, you don't own the data. Someone else is going to deallocate that data. When it is the box, when you drop the box, it will deallocate it, but it's hiding the fact that you don't know the size. So there is a way to work around all those size limitations I was talking about earlier by putting them in a box. We're now gonna hit the last fun part that I really wanted to talk about, which is async await. And then you guys will have been given a taste of all of the cool bits of Rust, and enough that you go and try to use them and you bang your heads against the wall of why is it not working like I meant to. So when we say fearless concurrency, we really mean fearless concurrency. And a lot of Rust applications are written so multi-threaded you can't even tell where the threads start and stop, and it's totally mixed in. They standardized in the Rust language fairly recently, like 2 years ago, these extra keywords, async and await, that are extra thready. What an async function, what putting async in front of a function does is it actually changes the function signature, and there's a way to write an async function that doesn't use the keyword but achieves the same thing, U64. It actually changes the return type of the function to be of type future, where this is an associated type that you can do. You don't really need to know what that does, but I'm telling it that the thing that the future returns is U64. Input times input. Why is it mad at me, Shane?
You have to do import future.
Thank you. So I'm saying, why is it mad at me, Shane?
Full box future maybe. Right, because that's why async tray can't be used on this instance.
Pretend this is what it's doing, because that is roughly what it's doing, but there's a lot of pedantry in there that it's handling for you. So what actually happens is your function returns instantly when your function's invoked, but what your function returns is not the result of running your function. Your function returns an abstract state machine that represents how to run the code that function represents, which then some other piece of code can call like a task manager to make incremental progress on it. So the way that this generally works, I'm going to jump down to the bottom of this function. I have main here, and I said async main, and I'm wrapping it in Tokyo main. Tokyo is far and away the main async executor that people use. Rust decided to separate out the executor from async await itself. What is the executor? In this case, I'm saying Tokyo main here. Before my main is called, Tokyo is going to hit the actual main. It's going to generate a thread pool. It's going to generate a thread for every single one of the logical cores on my processor. It's going to set up a task queue of async tasks. And then as futures are returned to that executor, it will dynamically schedule them between those threads, enter and exit them exactly like a work-stealing multi-process system. So now, anytime that there's an await point in my program where I say .await, what's actually happening there is I'm returning execution all the way up to the Tokyo executor, and it will decide whether to continue running my task, run someone else's task, swap where my task is running on what thread, move it around, do all kinds of crazy shit. This lets you write some insanely parallel, insanely efficient code. This is actually like the magic smoke that lets Actix be the fastest web server out there. A very common paradigm to do here is that these async tasks are incredibly cheap to make. If I was in a regular threaded ecosystem, actually generating a thread from the operating system, creating that thread, passing through the onus of moving data to it, and then joining that thread again, that will, no matter what, almost take 4 milliseconds on Linux. There is so much that has to happen to go through the operating system to create a thread. This is what a lot of people refer to as green threads, where spawning these tasks is free. The threads already exist. The Rust compiler is making sure that the memory that is needed to handle all this is as minimal as possible. There's no data races. There's no race conditions. Everything that can be on the stack will be on the stack. It's hyper efficient. And it means that you can do things where I write a web server where every single request I get in, instead of spawning a thread, I spawn a Tokyo task. And I start an entire new task handed up to the executor to run that particular request. So then I can write very logical code of okay, I got this request. I'm going to await data from this server. I'm going to await data from this server. I'm going to combine those two together, and I'm going to return that, and that will actually be the result of processing the request. I hand that whole state machine up to Tokyo, and Tokyo actually then executes it and runs it for me. That was a whole pile of information. Let's see what that actually looks like. So here's an async function. It takes in the number, it squares the number, and returns the number. As simple as possible. It doesn't need to be async. I just wanted a very simple async function. So if I actually try to just call that function with nothing, and I just say square 2, I get back this insane fucking type. Yeah, I get info future output equals U64. That I can't do anything with that. I don't know what to do. What I can do is I can pass it into this thing from this crate, futures executor block on this future. What this is doing is in the current thread, it's just going to keep running that future. Anytime that future returns at an await point, it just calls it again, says keep going, just keep going, and my current thread will block until that future returns. And then I actually get the result of squaring it back. So that's a way to, in synchronous code, I can call an async function, and I'm just going to block my current thread until it returns. You almost never want to do that, but if you have to, that's how it looks like. So here's what it looks like now to do it right. In an async function, I'm allowed to use this await keyword. And the await keyword ties into the future that gets returned and bubbles all the way up to the executor and says, here is a pause point in my task where you can take all the data that my task has on the stack, put it in a little state machine, set it on the shelf, run some other task, and then you can resume my task when you want to. Here is a breakpoint in my program. So right here, I can just say result equals U64 square input, and then dot await is saying block, but it's not actually blocking. It's just returning to the executor and letting the executor run other tasks if there's something else going on.
It's yielding until the future is available.
Yeah, it's yielding until I can make progress. There are some extraordinarily efficient crates in Rust that make incredible use of .await at the syscall level with the operating system by using the better version of file reading, where you say, hey, Linux, read this file for me, and you tell me when you finish loading the file into memory, and then that syscall will return, and that syscall will actually hit the await correctly, so that you don't ever sit polling waiting for it, but the executor can know when to actually resume progress on your task from the operating system. So the executor can be told from the operating system when your task is unblocked, instead of it ever having to, in a hot loop, check. That's really where await shines above and beyond, is in IO bound tasks, whether that's disk, whether that's network. The low-level Rust async libraries that implement those things have implemented the syscalls in the hyper-modern, hyper-efficient way, where there is no polling, and the operating system will actually notify the await for you. And there is no less overhead way to do it. Rust has the fastest web server, and this is how. Here's a fancier version of it. So I'm making a vector of nothing, and you notice I'm not specifying the type here. I don't actually have to specify the type on this line in any way. Rust is figuring out what the type has to be based off of what I pass into the push operation on the vector further down. We haven't really shown that off, but Rust's type inference is like, if Rust can figure out what the type has to be in any possible way, it will infer the type for you, which is pretty sweet. And you only have to put the type when you have to put the type. So I'm going through the values 0 to 100. I am creating a set of futures. At this point, no actual multiplication has happened. All I have set up is a list of 100 tasks that when those tasks are awaited, the multiplication will happen. I can now say futures join all to take this vector of tasks and combine it into one task where when this task completes, all 100 multiplications have been completed. And then I finally await the joined vector of futures, and that will return me a vector now of the result of every single one of those multiplications, and that will be completely simultaneously multi-threaded across all of the threads as efficiently as possible. That's pretty badass. The two major operations, when you think about like things we want to do with futures, join is a very common one. Like I need to await this thing, I need to await this thing. I'm going to await them in parallel. When they both complete, I would proceed with the results of both of them. That's very common. This join all one does that with a vector. Like you pass it in a vector, it returns me a vector of all the results. There's other versions of join that's like a macro where I can join three things explicitly and it will return me a tuple of the three things that I awaited. The other really common one that you want to do is select. So select is I am going to simultaneously await these two things, and whichever one returns first, I will proceed execution with that. There's this select macro in Tokyo that kind of looks like a match statement gone wild, but it's saying I'm awaiting future one. When future one returns, assign the result of future one returning to the variable res1, and then this method, closure statement, whatever you want to call it, will execute and actually print res1. This will print res2. I'm just racing these two threads. Whichever one returns first will get printed. That's great. That's cool. Here's what? Yes, and will be deallocated. When I stop, I can stop at any time executing the future, even if I don't execute it to completion, and drop it, and everything will be deallocated correctly, and everything will be memory safe. A thing that will confuse the living shit out of you at some point in Rust is I write an async function, and I have like a local variable here. Yeah, I have a local variable here. What am I gonna do? I'm gonna say let b equals. I'm gonna say string here, but string's not actually gonna do it. I don't know what type off the top of my head would be good, but I'm gonna say results2 equals square 4 dot await. Shane, what's the type that's not send? RC, right? Yeah, I should be able to do RC new 0 like that. I need it squared, not this. And I haven't said use RC, so here's the other syntax for it. Standard RC is the module like that. I think this will fail to compile. If it doesn't, something's gone wrong. Oh, it compiled. I don't know an easy way to manifest the error I'm talking about, but I want to explain what the error is briefly. Between every single one of these await points, Rust has to be able to pause your function, take all of the memory that exists on that function, and put it in a container, and then that might be moved to a different thread. Which means that if you have an intermediate local variable in the middle of your function, which is not safe to be moved to another thread, you can't await. And Rust will tell you, hey, you have a variable on the stack that isn't safe to be moved to another thread, and you're trying to split that local variable, which I can't move between threads, across the wait points. I think right now this is technically okay because it knows that. Yeah, it knows that no, this RC hasn't leaked anywhere else. I would have to create a type that was expressly not send to kind of manifest the bug I was trying to show you guys. But Rust is smart enough to know that, you know, it has to be able to pause your program, and the next thread that the executor resumes your program on might not be the thread that you used to be on. So a way I could try to manifest it right now, if I really cared, I could try to use some thread local storage. If I actually tried to use the like standard memory thread local storage API, then it would definitely start screaming at me. But I will pause there. I will end. I will say here's actually executing that program, and it does compile, it does run, and this is that's the result of squaring all those numbers we were talking about. And then the got2 here is the two threads we're racing. And as I run it, sometimes one will win, sometimes two will win. That's pretty cool. Okay, only 50% overtime. Turns out both of these needed to be an hour and a half, and I was consistent about that. I will call it there. Thank you, everybody, for hanging on for extra time because that's super fun.
Ask one more question.
Yes, I will keep answering questions.
So await and async are keywords of the language, but Tokyo is a crate that tells it how to do the thread pool.
Yes, and this is because Rust figured out an API for async and await that they were completely happy with. And they were like, this implementation for async and await is good for everybody universally in all circumstances. The same cannot be true of the executor that actually does the multi-threading. So Tokyo is the best crate for multi-threaded executor on Windows, Linux, Mac OS in the cloud. Tokyo can't run on a microcontroller. There are async executors for microcontrollers that implement a full RTOS for you and will do multi-threaded async await code on microcontroller land. There is a async executor that works in WebAssembly and does pseudo multi-threaded for you, even though it's being run inside of JavaScript in a fundamentally single-threaded environment. And so there are different flavors of executor out there in the ecosystem for different purposes. There is one called Async Standard, which is like an attempt at creating a standard library executor. I think more people use Tokyo. There's kind of a war back and forth between Tokyo and the standard library, and Tokyo refuses to have a stable API yet. Tokyo is bleeding edge, and they're like, we will do anything that will make it faster or higher performance or better, including API breaks. They still Semver the versions completely. You can still use the old versions, but they continue to evolve that crate as fast as possible. And they're like, no, we don't want to become part of the standard library while we're still evolving our API. Like, we want to be a truly stable API before we end up in. One of the really annoying things in the Rust ecosystem right now is if you try to write an async crate, there are some things that you want to do, like spawning a task, which there is not a universal way to do amongst all executors. Tokyo has a static function I can just call Tokyo spawn task, or Tokyo task spawn, something like that. And I will just pass it a closure, and it'll let me do that. In doing that, there's a heap allocation. There are async executors that are written on microcontrollers where there is no heap. And so the ways that they spawn tasks, all tasks have to be spawned up front before the executor starts running. So you have to create all of your tasks on the stack before starting the executor. So there's not a truly universal way to spawn a task that works with all executors because of, people really care in different points. I do want to talk again just a little bit, like Rust can make this async state machine that represents the different paths of your code with these different save points where the memory of that function can be set aside. One of the truly amazing things about Rust is that whole state machine is actually implemented as an enum. And the size of the future that exists is the size of the largest one of those save points. And it will at compile time create a stack object or a heap object, depending on how it's invoked, that is guaranteed to fit the total memory for your future. So there can be an allocation up front for creating your future, and then after that, your entire future can execute with no memory allocation because each state reuses the memory of the previous state. And like the variables between await points will be overlaid on top of each other, and that's just magic. Like this is, again, the compiler knows so much of compile time. It knows what's thread safe. It knows the size of things or what it doesn't know the size of. Because it has so much power, they were able to implement truly the most efficient version of async await that anyone has. Like there are coroutine libraries in C. There are C++ attempts at this. I don't think any of them actually is as efficient as Rust's because the compiler can do so many compile time optimizations on what that future actually is.
So the future actually contains all of the memory of the task? The future itself contains that?
It contains all the stack memory of it. you can then have like pointers to heap
Right.
memory for it, but the future will be large enough to fit the stack memory of your function within it at all times, at all pause points.
So the async functions just being functions that return futures, that seems very similar to JavaScript's like promises.
Yep.
So then is the await keyword basically just calling a function on the future trait?
No, but yes, but no.
Okay.
What the await keyword doesn't call a function on the future trait. The await keyword yields the future up to the executor. The executor then calls the function on the future trait. So the actual name, we can look this up. Rust future trait. The name of the function is pull. And this is the actual, to be a future, you have to implement this pull function, which takes a and mute reference to self. Pin is a trait we haven't talked about yet, but pin says this memory is not allowed to move. If I pin a vector, that vector is not allowed to resize and move its storage to somewhere else. The address must be consistent, so you can pin and unpin memory. That's another thing that exists. So to pull something, you take a pinned mutable reference to yourself and this other context object, which lets you do some fancy things, and then you return a pull of type self output. Pull is in of itself an enum that tells you I'm ready, this future has finished, and here is the type, or pending. And so that is the function that the executor ends up calling on the future, but instead of await calling that function, await hands the future back to the executor, which then calls it when the executor wants to.
Okay, so there's not like a concept of like, I'm thinking like the promise was rejected, if it's just pending and ready. Or
what you do, Rust does type encapsulation. I would have a future where the return type of that future is a result. So if we go back to VS Code and I wrote if I wrote async function can fail, this can either return option would be the simpler case, option U64, and if anything goes wrong, it returns none. Otherwise, it returns the thing. So again, you like it's ready. It might not be ready with the result you wanted, but it will be ready with something which will tell you what happened when we tried to run that future. I'll take another question. Are we good?
There's gonna be people who learn this language first that are useless everywhere.
Yeah.
I frequently feel useless in C++ after writing.
I never want to spawn a thread in another language again. Like it does it all for you. It makes it safe. I mean, like you will get into these nightmare situations with Rust. I will say, like Rust can be incredibly challenging to write because you will start a program. You have this very complicated idea of here's what my data is going to be. Here's how my threads are going to be. You're going to go and you're going to go and you're going and you're going to get like 99% done, and then you're going to try to put the last function call in place, and the compiler will tell you no. And because everything you did up to that point was valid, but then you access the memory in two places. And why in your giant sprawling level of a program that is unsafe to do can be super hard to understand why. But the compiler will be right. But then figuring out what you have to do to your program to actually make it safe can be a nightmare because you've created this whole multi-state async thing, or this thing's being passed through 5 layers, yada, yada, yada. And the whole time the compiler's like, okay, I can assume it's safe, I can assume it's safe, I can assume it's safe. And finally you do something where like through that entire chain, an extra constraint has to be in place for you to do the thing you're wanting to do. And the compiler's like, no, I can't guarantee that anymore. And when you get in those situations, knowing what the right thing to do is can be super, super hard. My very, very strong recommendation is to clone your data. This is kind of the like Rust emergency hatch. Like if you're ever in a situation where the compiler won't compile, just make a copy of the data and pass the copy along. And you break the like ownership chain. It's like a fuse in it. And you're saying, okay, I'm sorry, I don't know how to guarantee the lifetimes. I don't know how to guarantee the safety or the reference is still valid and yada, yada, yada. But if I just pass you a copy, that's safe. And you know, Rust is only really pedantic when it's trying to make sure that you're not copying anywhere and it's referencing the same memory and everything's going fine. So that's the escape hatch. You'll find there's like 5 of those in programs I've written where I just gave up and I was like, okay, I'm sure there is a way to make this perfectly memory efficient without a single wasted byte, but I don't know what it is. So I'm just going to make a copy here and I'm safe and my program compiles. Just a pro tip. Give up and call clone. All right, I'm calling it. Meeting's over.